A Gothic cathedral stands against the sky, built without steel or computers. The secret to these impossible structures was not magic, but geometry. Medieval engineers mastered a set of geometric rules that transformed stone and mortar into breathtaking cathedrals, unbreachable castles, and revolutionary machines. By the end of this journey, you will understand how ancient geometric principles still influence the buildings around us today. How did a simple compass allow them to calculate proportions that defied gravity? Why were certain shapes considered sacred? We will uncover the precise language of lines and circles they used to turn architectural dreams into reality. What does it truly mean to build something that lasts 1,000 years? A master mason's most important drawing was not a detailed plan, but a series of lines scratched into a flat stone table or a wooden board. With just a compass and a straightedge, he could generate the entire proportional system for a cathedral. This was not seen as a human invention, but as a process of discovery. The circle, drawn with a fixed compass, represented the divine perfection of the heavens. The square, derived from the circle, symbolized the earthly realm. By combining these pure forms, the mason believed he was literally bringing heaven down to earth, uniting the spiritual and the material in stone and mortar. Saint Augustine himself wrote that numbers and geometric forms existed in the mind of God, and that to build with them was to participate in a sacred act. This profound belief meant that every decision, from the overall length of the nave to the curve of an arch, was guided by geometric rules considered to be universal and holy. Construction became a form of prayer and the building site a kind of outdoor temple. This spiritual drive demanded absolute precision, pushing craftsmen to achieve a level of accuracy that mere practical necessity might not have required. Their unwavering faith in this divine language gave them the confidence to attempt the impossible, and the key to speaking this language fluently lay in a small collection of remarkably simple tools. A craftsman's calloused hands hold a simple metal compass, its sharp point anchored to a flat surface as the other leg swings in a perfect, unbroken arc. This was the absolute starting point. Alongside it lay the straightedge, a simple strip of wood or metal with a true edge. With nothing more than these two tools, a master mason could generate the entire geometric vocabulary of a cathedral. This was not a matter of drawing a picture, but of unlocking a system. With immense skill and a deep intuitive understanding of geometry, he could bisect any angle, divide any line, and construct any polygon required for the design. The compass determined the sweeping radii of arches and the delicate curves of window tracery. The straightedge guaranteed the absolute straight lines of walls and the precise angles of buttresses. This elegant simplicity masked a profound capability. The same geometric pattern, inscribed on a small tracing floor, could be replicated perfectly across a vast construction site by any mason who knew the rules. There were no detailed blueprints to misread, only a shared language of lines and circles. This reliance on fundamental tools forced a deep understanding of geometric principles. It was a process of discovery, not just drafting. The precision they achieved did not come from advanced technology, but from a masterful application of the simplest forms. And from these basic shapes, they derived a set of governing ratios that gave their structures both breathtaking beauty and unshakable stability. That same compass, tracing a perfect circle, could unlock a secret harmony found throughout the natural world. Look at the spiral of a nautilus shell, the arrangement of seeds in a sunflower, or the branching of a tree. All of these follow a precise mathematical relationship known as the golden ratio. This special number, approximately 1.618, creates proportions that feel inherently balanced and beautiful to the human eye. Medieval master builders may not have called it by name or written equations for it, but they understood its power intuitively. They discovered it through the pure geometry of the pentagram, a 5-pointed star that can be constructed with nothing but a compass and straightedge. The lines of a pentagram intersect at points that divide each other in this exact golden proportion. This made the pentagram a powerful geometric key, a direct link to a universal law of beauty. Historians studying cathedrals like Chartres find this ratio echoed everywhere. The entire facade, from the ground to the tip of the spires, often fits within a golden rectangle. The placement of windows, the height of arches relative to their width, even the overall floor plan of the nave and transepts, all frequently adhere to these harmonious dimensions. This was not a random aesthetic choice. It was a deliberate effort to build a space that felt divinely ordered. When you stand inside such a cathedral, the proportions resonate on a subconscious level, creating a sense of peace, stability, and rightness. This harmony also enhanced the building's structural integrity, as balanced proportions naturally distribute weight and stress more effectively. By leveraging a ratio woven into the fabric of nature itself, medieval engineers achieved a perfect blend of art and science. They built structures that were not only physically sound but spiritually resonant, captivating the human spirit across centuries. The facade of Notre-Dame de Paris is a symphony in stone, composed entirely of perfect squares. Look up at its famous west front, and you are seeing the ad quadratum technique made manifest. Medieval builders began with one master square. By rotating and subdividing it, they generated a cascading grid that dictated every proportion you see. The width of the entire facade equals its height to the base of the towers. The central rose window is perfectly framed by a square, and the famous twin towers themselves rise from a square footprint. This was not an artistic whim. This geometric rigor provided the cathedral with a deep, underlying stability. The forces of gravity and wind were channeled through a predictable, balanced framework, preventing the structure from twisting or shearing under its own immense weight. But the true magic of this system is seen in the cathedral's most breathtaking features, its rose windows. These are not just circular stained glass, they are massive stone wheels, each a complex web of geometric tracery. The radiating patterns of stone do more than hold the glass. They act like the spokes of a bicycle wheel, distributing the enormous downward thrust of the wall above outwards towards the supporting buttresses. This transforms a potential weak point, a giant hole in the wall, into a masterpiece of structural engineering. The colored light flooding through these geometric windows was seen as divine illumination, a literal and metaphorical light of heaven, made possible by the cold, hard logic of circles and squares. This union of spiritual aspiration and geometric precision gave builders the confidence to reach even higher, to push stone and mortar to its absolute limits in a daring race towards the sky. This race toward the heavens came with a terrifying price. As walls grew taller, the immense weight of the stone created a powerful outward thrust that could shatter the very walls meant to support it. The traditional rounded arch, inherited from the Romans, was a bottleneck to height, pushing its load outwards and demanding ever thicker walls to contain the force. The solution was a geometric revolution hidden in the elegant form of the pointed arch. Unlike its semicircular cousin, the pointed arch is born from the intersection of two circles. This simple geometric trick fundamentally changed how a building carried its weight. The steeper angle of the pointed arch channels more of its load vertically down into the supporting piers, drastically reducing the dangerous sideways thrust. This meant walls could be taller and the spaces between them wider, flooding the interior with light, but the innovation did not stop there. To support the vast stone ceilings of these new, taller naves, engineers developed the ribbed vault. Picture a skeletal framework of stone ribs, each one a pointed arch, intersecting high above the floor. These ribs were constructed first, creating a geometric template that the lighter infill stones were then fitted into. This was not just a decorative choice, it was a brilliant structural system. The ribs concentrated the ceiling's load and directed it precisely down to specific points on the floor, points that could be reinforced with massive piers and, most importantly, met by the next great geometric invention waiting outside. The ambition to build higher was a dangerous dance with gravity, and geometry provided the steps. At Beauvais Cathedral in France, they pushed this principle to its absolute limit. Its choir soared to a dizzying 157 feet, the highest vaulted ceiling ever attempted in a Gothic cathedral. For a few decades, it stood as a breathtaking monument to geometric confidence. Then, in 1284, part of the choir collapsed. The geometric calculations for the height and thrust were sound, but the physical limits of the stone and mortar had been exceeded. It was a stark lesson that geometry could guide ambition, but it could not defy the fundamental properties of materials. This cycle of trial and error, guided by the unwavering rules of the compass and straightedge, allowed builders to refine their designs generation after generation. They were using geometry to conquer gravity itself, and their most powerful weapon in this battle was still to come, a simple, stable shape that would shoulder the entire weight of the sky. That simple, stable shape was the triangle. While the pointed arch conquered vertical forces, it was the triangle that mastered the sideways thrust, threatening to tear these stone giants apart. Look up into the shadowy heights of a cathedral's roof, and you will find a hidden forest of wooden beams. These are the trusses, and their design is a masterpiece of triangulation. Each truss is a skeletal framework of timbers locked together into a series of rigid triangles. This geometric configuration is fundamental. A triangle cannot be distorted without breaking one of its sides. When the heavy roof tiles press down, the triangular trusses distribute that immense load evenly along their members, channeling the force straight down the walls instead of pushing them outward. This inherent stability was the secret to spanning such vast spaces without internal supports. But the most dramatic use of the triangle is outside the building, in the iconic Flying Buttress. Picture a graceful stone arm, arched like a bridge, leaning against the cathedral's high walls. This arm is not a solid block, it is a carefully engineered triangulated structure. Its own weight and shape create a counter-thrust that pushes back against the outward force from the vaults inside. At Salisbury Cathedral, you can see this principle in its most elegant form. The flying buttresses there are not just brute supports, they are precisely calculated arcs, their angles determined by geometry to intercept and redirect the line of thrust from the high vaults down to the massive exterior piers. This turned the entire building into a dynamic system of balanced forces, a stone mechanism where every part worked in geometric harmony. By understanding and applying the immutable stability of the triangle, medieval engineers could confidently peel away the heavy, solid walls of the Romanesque past. They replaced them with vast, luminous curtains of stained glass because the skeleton of the building was now on the outside. The geometric integrity of the triangle enabled the Gothic revolution of light and height, proving that true strength often lies not in mass but in the intelligent arrangement of form. This geometric thinking did not stop at the cathedral's walls. It extended across the entire building site, governing the very layout of a sacred complex. While the cathedral reached for the heavens, the castle was firmly rooted in the earth, a brutal application of geometry for survival. From above, a fortress like Crac des Chevaliers reveals itself as a masterpiece of defensive planning, with multiple rings of walls perfectly nested within one another. This concentric design was a geometric trap. An attacker breaching the outer wall would not find safety, but a deadly killing zone completely exposed to arrow fire from the even higher inner walls. Every curve and angle was calculated to eliminate blind spots and create overlapping fields of fire. The straight, flat sections of wall between towers were deliberately kept short, ensuring that defenders in one tower could see and protect the base of the next. This created an interlocking web of defensive sightlines, a geometric net that no attacker could easily slip through. To lay out these precise foundations, surveyors relied on a simple but brilliant tool called the Groma. This device, essentially a cross with weighted plumb lines hanging from each arm, allowed them to sight perfect right angles across vast distances. With it, they could ensure that curtain walls met at exact 90-degree corners and that towers were positioned with mathematical accuracy. This precision was not about aesthetics, it was about structural integrity and tactical superiority. A wall built on a geometrically true foundation was stronger and more stable, and a tower placed at the correct angle gave its defenders the clearest possible shot. As siege technology evolved with the advent of cannons, the geometric forms of fortifications evolved in response. The tall, relatively flat walls of earlier castles were vulnerable to cannonballs. The solution was the star-shaped bastion, a form born entirely from geometric calculation. Its low, sloping walls and sharply pointed projections were designed to deflect cannon fire away from the fortress, while the angled faces allowed defenders to rake any approaching army with enfilading fire from their own guns. This relentless geometric innovation turned castles into immense stone puzzles of defense, where every line and angle had a life or death purpose. The same principles of proportion and alignment that created spaces of spiritual harmony were now being used to orchestrate the most efficient forms of destruction and protection, proving that geometry was the ultimate tool for shaping both peace and war. That same geometric genius that built cathedrals and castles also arched over rivers and valleys, bringing communities together. Medieval engineers applied their sacred principles of the circle and the triangle to the very practical needs of bridges and aqueducts. A stone bridge is a cathedral in miniature, a structure where every block must work in perfect harmony to resist the relentless flow of water and the constant pounding of traffic. The semicircular arch was a trusted form, but for spanning wider rivers, builders developed a more refined shape, the segmental arch. This arch is a shallower, flatter curve, a section of a much larger circle. Its geometry was a brilliant adaptation. By using a flatter arc, the bridge could have a longer span without needing to build towering, expensive piers in the middle of a fast-moving river. It also allowed more room for floodwaters to pass underneath, preventing the structure from being swept away during a storm. This curve was not just a guess, it was a precise mathematical form, often approaching the elegant curve of a parabola, which naturally distributes weight along its entire length. How did they plot such a perfect, massive curve on a muddy riverbank without modern surveying tools? The answer lies in a simple cord and two stakes. A master builder would drive a stake at the center of where the arch would rise. Then, attaching a cord to it, he would use the tension in the line like a giant compass, tracing the perfect arc for the masons to follow. This on-site geometric construction ensured that every stone cut for the arch would fit precisely, locking together under compression to create a structure of immense strength. The famous Pont d'Avignon in France, though only partially standing today, is a testament to this geometric rigor. Its series of robust, perfectly shaped arches once stretched across the powerful Rhone River, carrying people and goods for centuries. Each arch was a self-supporting unit, and the entire bridge functioned as a continuous geometric chain, its stability derived from the unyielding logic of its curves. This application proves that medieval geometry was not confined to the sacred. It was the essential, practical language of public works. The knowledge to build such enduring structures was far too valuable to be left to chance, so masters developed a powerful system to ensure their geometric secrets would survive long after they were gone. Behind the soaring stone and stained glass lay a world of fierce secrecy. The master mason's geometric knowledge was his most valuable possession, a treasure guarded not in a vault but within the closed circles of the guilds. These were not just trade unions, they were sworn fraternities of builders who protected their methods with an almost religious zeal. In a dimly lit lodge, a master would teach his apprentices not from a book, but through direct hands-on demonstration. Complex principles for setting out a vault or designing a perfect spiral staircase were transmitted orally and through practice, a living chain of knowledge passed from one generation to the next. This ensured that only a fully initiated craftsman, one who had proven his skill and loyalty, could replicate the most advanced techniques. There were no detailed written plans to be stolen by a rival town or an unworthy builder. The entire system was designed to maintain a monopoly on the craft, making the guilds indispensable. To convey methods without written records, masters developed a symbolic language. The tools of their trade, the square and the compass, became powerful emblems. The square represented morality and right action, the earthly realm of the builder. The compass symbolized the divine circle of the heavens and the spirit of intellectual inquiry. Together, they represented the perfect union of the material and the spiritual that the cathedral itself embodied. Coded drawings, often simple-looking diagrams of overlapping circles and squares, held the keys to entire structural systems. To an outsider, it was just a pattern. To an initiated mason, it was a precise recipe for proportion, a geometric code that could generate the entire elevation of a wall or the complex curvature of a ribbed vault. Historical records from the time speak of this knowledge with profound reverence, calling the craft a sacred mystery. One medieval text describes the master mason as one who possesses the secret of secrets, a man who works with the mind as much as with his hands. By wrapping their expertise in this veil of esoteric tradition, the guilds did more than just protect their jobs. They fostered a culture of intense, controlled innovation. Each generation built upon the geometric foundations of the last, refining and improving within a protected framework. This is why the Gothic style evolved so rapidly and so brilliantly across Europe, a conversation in stone conducted by a select few who spoke the same geometric language. The very buildings we admire are therefore more than just architecture. They are immense, three-dimensional puzzles, their solutions locked within the silent geometry of their stones. Within the stone heart of a castle tower, a spiral staircase coils upward in a perfect, continuous curve. This is not merely a set of steps, it is a geometric marvel, a helix carved from stone. To design it, a master mason turned to the volute, a spiral pattern found in nature, from the unfurling of a fern to the chambered shell of a nautilus. These organic forms follow a progression of numbers now known as the Fibonacci sequence, where each number is the sum of the two before it. While medieval builders did not write out this sequence, they could replicate its elegant, expanding spiral using only their compass and a series of rotating squares. This natural geometry gave the staircase its fluid, unbroken form. But the true genius lay in the precise calculation of each step. the mason had to ensure everyone had an identical rise, the vertical height, and run, the depth of the tread. Any inconsistency would create a tripping hazard or a weak point in the structure. They achieved this uniformity not with complex equations, but through geometric templates and a profound practical understanding of proportion, ensuring the entire spiral was both stable and safe to climb. This design was a masterpiece of efficiency. In a cramped tower, a spiral staircase takes up far less space than a straight flight, and its central stone column acts as a powerful backbone, supporting the entire structure. There was also a brutal tactical advantage. A right-handed defender standing on the steps above would have full freedom to swing his sword, while an attacker climbing up from below would find his own weapon constantly obstructed by the central pillar. This geometric form literally built the high ground into the architecture. The ultimate expression of this principle can be found at the Château de Chambord in France. Here, two independent spiral staircases are interwoven into a single, breathtaking double helix. Two people could ascend and descend simultaneously, catching glimpses of each other through strategically placed openings, yet their paths would never cross. This was a feat of geometric planning so advanced it seems to defy the physical space it occupies. By solving the intricate puzzle of continuous curvature, medieval builders infused even the most functional elements with a sense of wonder. Their ability to scale this geometric thinking from a single step to an entire fortress demonstrates a mind-bending versatility, a skill they would need to confront the gravest threat any stone structure could face. High above, a stone net of ribs and bosses captures the sky, a ceiling that seems to float without support. This is the Gothic vault, the ultimate expression of medieval geometry in 3 dimensions. To stand beneath one is to witness a structural magic trick where the weight of the roof is not a burden, but a force choreographed along elegant, curving paths. The secret was a process of generative geometry. A master mason began with the simple pointed arch, the basic unit of strength. He then repeated and intersected these arcs, creating a skeletal framework known as rib vaulting. This framework was everything. The ribs were built first, acting as a permanent scaffold that defined the vault's shape. Once the ribs were locked in place, the skilled workers could fill the spaces between them with thinner, lighter stones. This meant the entire ceiling was not a solid, crushing mass, but a carefully engineered shell. The ribs channeled the immense weight along their specific curves, directing the forces precisely downward to the columns and piers below. This geometric control allowed interiors to become taller and more expansive, transforming dark, cavernous spaces into ethereal halls of light. But how did a mason translate a small drawing into a perfect, massive curve overhead? The answer lies in the tracing floor, a large, flat surface of plaster or stone in the mason's lodge. Here, the full-scale profile of every single rib and arch was scratched directly into the floor. This life-sized geometric drawing was the master template. Craftsmen would create wooden molds based on these lines, ensuring that every stone block cut for the vault would fit into its designated place with absolute precision. It was a breathtaking feat of scale and accuracy, a direct transfer of geometric theory from a flat plane into soaring, 3-dimensional space. This system allowed for incredible creativity. At Gloucester Cathedral, you can see this evolution reach its stunning conclusion in the cloister's fan vaults. These are not just ribs, but a breathtaking cascade of stone that resembles a half-opened fan. Each fan is a series of identical concave curves, all springing from the same point on the wall and all based on the same compass-drawn radius. The geometry is perfectly repetitive, yet the visual effect is one of organic, flowing abundance. The fans lock together to form a continuous, incredibly strong shell, proving that the most decorative forms could also be the most structurally sound. The ceiling was no longer just a roof, it had become a stone tapestry woven from geometric threads, a canvas where mathematics and art became indistinguishable. This same inventive spirit, applied not to stationary stone but to moving parts, would soon set in motion a revolution of gears and levers. The same geometric principles that locked stones into place were also harnessed to set them in motion. A trebuchet's throwing arm does not swing randomly. It follows a precise circular arc dictated by the pivot point of its axle. The length of the arm and the weight of the countermass were not guesses, they were variables in a geometric equation for destruction. Engineers discovered through repeated use that a certain ratio between the short and long sections of the arm would maximize the transfer of energy, slinging a massive stone in a high, parabolic arc over castle walls. This trajectory was not calculated with algebra, but mapped through the physical geometry of circles and levers, a brutal application of the same compass used to trace a rose window. This mechanical genius extended to the construction site itself. To lift a multi-ton block to the top of a cathedral wall, medieval workers used giant cranes powered by treadwheels. The boom of the crane, its angled arm, was a study in applied trigonometry. Its angle determined both the height it could reach and the horizontal distance it could cover, a careful balance to place each stone exactly where the geometric plan demanded. The pulley systems within these cranes used multiple wheels to redirect force, a practical application of circular motion that drastically reduced the human effort needed to raise immense weights. Surviving manuscripts like the famous sketchbook of Villard de Honnecourt are filled with these machine diagrams. They are not just pictures of devices, but geometric proofs in action, showing the clear lines and circles that govern leverage, rotation, and balance. A simple circle could become a winch, a lever could become a catapult, and a triangle could become the stable base for a tower crane. This was geometry liberated from the page, a dynamic force that amplified human strength to literal superhuman levels. The intellect that designed a machine to hurl a boulder was the same one that calculated the curve of a vault, proving that the line between architect and engineer did not exist. This versatile understanding of form and force would soon be scaled up once more, from individual machines to the grand design of entire cities. The same geometric logic that structured a single building was scaled up to design entire cities. Walled new towns like Aigues-Mortes in France present a startling sight from above, their street plans a perfect grid of straight avenues intersecting at rigid right angles. This was not an organic sprawl, but a deliberate act of geometric imposition. Using their trusted Gromas and sighting rods, surveyors laid out these urban grids with the same precision they applied to a cathedral's foundation. The entire town became a geometric module, a series of identical rectangular plots that could be allocated fairly to settlers, ensuring equitable land distribution and simplifying taxation. This orderly layout was a tool of control and efficiency. Straight, wide streets allowed for the rapid mobilization of soldiers to the walls in case of an attack. They also facilitated trade, as merchants could move their carts easily from the main gates directly to the central marketplace. This marketplace was never placed at random. It was almost always situated at the geometric heart of the town, the focal point where the main axes crossed. This central square was the community's living room, a space for commerce, public announcements, and social gathering, all made possible by its deliberate geometric placement. Across Europe, hundreds of these planned communities, known as bastides, were built. Their uniform grid plans were a physical manifestation of a feudal lord's authority and a desire for social harmony through mathematical order. To walk the streets of a bastide is to experience geometry as a daily reality, where every turn is a 90-degree affirmation of a planned world. This systematic approach to urban design created functional, defensible, and resilient cities, proving that geometry was the invisible framework for community life itself. This universal language of lines and circles was not confined to one region, however. It traveled, adapting to new lands and different dreams, transforming itself to meet the needs of empires and the ambitions of kings. The same geometric principles that ordered European cities were themselves shaped by a vast exchange of ideas spanning continents. Look up at the ceiling of a Moorish palace, and you will find a universe of interlocking stars, a complex web of polygons that seems to extend into infinity. This is the art of tessellation, a concept that flowed into medieval Europe through the cultural crossroads of Islamic Spain and the Mediterranean. In centers of learning like Cordoba and Toledo, Islamic scholars preserved and expanded upon the geometry of the ancient Greeks, adding revolutionary new concepts. Their texts, translated into Latin, became essential reading for the intellectually curious. The work of Al-Khwarizmi, whose name gives us the word algorithm, systemized algebra, providing builders with a new language for calculating proportions and stresses. This was not a mere borrowing of patterns, it was a fundamental enrichment of the European geometric mind. The iconic pointed arch, so central to the Gothic revolution, did not emerge in a vacuum. Its elegant, weight-channeling form had been perfected centuries earlier in Islamic architecture, from the mosques of Cairo to the palaces of Baghdad. Crusaders and merchants encountered these structures, and the concept traveled back to the north, where European masons adapted it for their own soaring ambitions. One of the most stunning imports was the muqarnas. These stunning, honeycomb-like decorations appear as stone stalactites dripping from ceilings and vaults. To the eye, they seem almost organic, but their construction is pure, rigorous geometry. Each muqarna's unit is a tiny, three-dimensional polygon, a squinch or niche based on precise geometric sequences. These units are then stacked and combined in infinite variation, creating complex, self-supporting vaults that seem to dissolve the solidity of the stone. European builders saw in this a new way to think about space and ornament. They adapted the underlying principles of the muqarnas, using its geometric logic to create more elaborate and decorative vaulting in their own churches and palaces. This fusion of knowledge transformed the architectural landscape. The geometric toolkit was no longer just about circles and squares, but now included 8 pointed stars, complex interlacing patterns, and sophisticated methods for subdividing space. This global conversation in stone and mortar proves that the greatest human achievements are rarely the product of one culture alone, but are built upon a shared foundation of discovery. To see this geometric fusion at its most sublime, we must finally turn to the ultimate expressions of this craft, the iconic structures whose secrets are written in the very angles of their stones. Beneath your feet, a single path unwinds across the stone floor of Chartres Cathedral, a labyrinth coiled into a perfect circle. To walk this path was to embark on a spiritual pilgrimage, a geometric journey toward a divine center. This intricate floor design is only the beginning, a single clue to the profound geometric code that governs every stone of this masterpiece. Chartres stands as a complete encyclopedia of medieval engineering, a structure where the sacred language of shape and number is written in full view. The entire west facade is a perfect square, its width from tower to tower exactly matching its height to the base of the rose window. Step inside, and the square appears again, defining the crossing of the nave and transept. The length of the nave itself is precisely 3 times its width, a harmonious ratio of 3:1 that echoes the Holy Trinity, turning the very floor plan into a theological statement. This relentless application of the square and circle, a technique known as quadrature, was the builder's ultimate tool for unification. they sought to square the circle, a geometric puzzle representing the impossible task of reconciling the finite, earthly square with the infinite divine circle. By weaving these two forms together in their proportions, they believed they were literally building a bridge between heaven and earth. This cosmic ambition guided the placement of every window and pier. The massive columns lining the nave are not spaced at random. Their positions are calculated so that on specific feast days, the sun's rays pour through the stained glass at precise angles, illuminating certain altars or symbols with celestial timing. The cathedral itself becomes a giant stone astronomical clock, its geometry synchronizing the rhythms of the church with the motion of the heavens. This was not just architecture, it was a cosmic diagram made tangible, a physical representation of a universe believed to be ordered by God's own geometric rules. Every choice was a deliberate act of faith expressed through mathematics, a quest for a perfection that could only be approached through the unwavering logic of the compass and straightedge. A master mason's geometric drawing, perfect on the tracing floor, was useless if it could not be transferred to the uneven reality of the land. For that, the medieval engineer turned to the Groma. Picture a surveyor on a windswept hill, his gaze fixed on a simple wooden cross mounted on a pole. From each arm of this cross, a plumb bob hangs perfectly still on its cord. By sighting along these vertical lines, he could establish a flawlessly straight line across hundreds of feet, or, by turning the cross 90 degrees, mark a perfect right angle. This humble device was the linchpin of large-scale construction, the critical link between geometric theory and physical stone. With it, a team could lay out the entire foundation of a cathedral or a castle, ensuring that the walls would be parallel, the corners square, and the structure stable from its very base. This geometric precision was not merely practical, it was often sacred. Many churches were meticulously aligned along an east-west axis, with the altar facing the rising sun, a symbolic orientation that required astonishing accuracy over the building's entire length. A misalignment of just a few inches at the foundation would grow into a catastrophic error by the time the walls reached the roof. The skill of the surveyor lay in preventing these compounding mistakes, using the unwavering truth of gravity in the plumb lines to impose geometric order upon the chaotic earth. In the layout of a vast monastic complex, this accuracy was everything. The church, the cloister, the chapter house, and the workshops all had to relate to one another within a harmonious geometric plan, a small city of faith drawn directly onto the landscape with stakes and string. This rigorous foundation, this invisible network of true lines and right angles, was what gave the later builders the confidence to execute their most daring artistic flourishes. The stability of the entire soaring enterprise rested on this first, precise act of measurement. A rose window is a frozen firework of geometry and light. Its complex web of stone and colored glass is not a random mosaic, but a radiating symphony of circles, each piece of glass a tiny, precise polygon locked into a lead frame. The stone framework itself, known as tracery, is where the mason's compass truly danced. He began with a master circle, then used the same tool to inscribe smaller circles within it, their intersections creating the delicate, flame-like patterns of the flamboyant style, or the serene, clover-like shapes of quarterfoils. Each of these stone ribs was a structural necessity, acting as a miniature buttress that distributed the wall's weight around the glass opening, bracing the entire assembly against the push of the wind. This geometric armature transformed a potential weak point into a source of immense strength. The true marvel is that every single piece of colored glass in the window, every red diamond or blue triangle, was individually cut to fit its unique position within this rigid geometric grid. craftsmen used metal templates derived directly from the master mason's compass drawings to ensure that each piece would slot perfectly into the lead cames that held the window together. This was a jigsaw puzzle of light, engineered on a monumental scale. Nowhere is this achievement more breathtaking than inside Sainte-Chapelle in Paris. Stepping into its upper chapel is like walking into the heart of a jewel box. The walls are virtually gone, replaced by towering panels of stained glass framed by the most delicate, lace-like stone tracery. The geometric precision of that stone framework is the only thing making this cage of light possible. It bears the load of the roof, allowing the walls to dissolve into a radiant narrative of biblical stories told in glass. The light passing through these geometric windows was itself transformed, broken into countless colored fragments that danced across the stone floor. This was seen as divine illumination, a physical manifestation of heavenly grace made possible by cold, hard geometric calculation. The windows became more than decoration. They were geometric sermons in light and color, teaching theological order through the universal language of shape and proportion. In this sacred space, beauty was not an accident. It was the direct and inevitable result of mathematical truth. The labyrinth at Amiens Cathedral is not a maze but a single, unbroken path coiling toward a center. Walking its geometric turns was a physical prayer, a pilgrimage in miniature that mirrored the soul's journey from the chaos of the world to the divine order of God. This path carved in stone is a perfect key to understanding how medieval builders used geometry as a language, one where every shape and number carried a profound symbolic weight. The circle, with no beginning and no end, was the universal symbol for eternity and the perfection of heaven. The square, with its 4 equal sides, represented the earthly realm, the 4 elements, and the cardinal directions. And the triangle, the simplest stable form, was a direct representation of the Holy Trinity, 3 distinct aspects united in one divine essence. When a master mason combined a circle and a square in his design, he was doing more than calculating a proportion. He was enacting a spiritual concept, striving to square the circle and bring heaven down to earth. This symbolic thinking dictated everything. The number of sides on a chapel was never arbitrary. A 12-sided baptistry echoed the 12 apostles, while an 8-sided structure reflected the 8 Beatitudes or the concept of resurrection, as Christ rose on the 8th day. The very floor plan of a cathedral, often in the shape of a cross, told the story of Christ's sacrifice to anyone who viewed it from above. This encoded meaning transformed a building from a mere shelter into a 3-dimensional Bible, a stone sermon that taught theology through shape and space. The geometric patterns were a silent language that even the illiterate could understand, a visual liturgy that guided the faithful through a sacred narrative. Why would engineers, focused on the practicalities of weight and thrust, concern themselves with such esoteric symbolism? Because for them, there was no separation. A structure that was symbolically sound, that reflected the divine order, was believed to be inherently more stable in a cosmic sense. The same geometric truth that ensured a vault would not collapse also ensured the building was a faithful representation of God's creation. This deep, intertwined purpose is what gave these structures their enduring power, making them feel not just built but ordained. To stand inside one is to feel the presence of a world where math and mystery were 2 sides of the same sacred coin, a world where the next architectural challenge was not just a test of skill, but a puzzle to be solved with this divine geometric language. The stone delivered to the building site was rarely perfect, a chaotic collection of irregular blocks. Yet from this apparent disorder, medieval engineers assembled perfect, enduring arches. Their secret was a set of geometric guidelines that transcended the flaws in their materials. They worked with stone of varying strength and timber prone to warping, but geometry offered a universal language to overcome these inconsistencies. A master builder did not need to test every single block. Instead, he relied on proven rules of thumb, geometric proportions that guaranteed stability. For any stone arch, its thickness at the crown needed to be roughly 1/10 of its span. This simple ratio, born from centuries of observation and geometric reasoning, ensured that the arch would channel its compressive forces safely downward, regardless of minor imperfections in the individual stones. This same principle of proportional design applied to the vertical supports. A massive column did not need to be a solid, wasteful monolith. By shaping a pillar with a base width to height ratio of 1 to the square root of 2, builders created a form that was perfectly balanced to resist buckling under immense loads, using stone with maximum efficiency. This geometric foresight is why so many medieval bridges still stand today. The Pont Vaillantre in France, with its 3 fortified towers, has spanned the river Lot for over 7 centuries. Its arches have weathered floods and wars, and its stonework has been repaired and modified countless times. Because each original arch was built to a precise geometric standard, later craftsmen could understand its logic and replace individual stones without compromising the entire structure. The geometry provided a timeless blueprint, a set of rules that allowed the bridge to adapt and heal across generations. This was the ultimate triumph of their ingenuity. They did not fight against the limitations of their materials, but used geometry to harmonize with them, turning nature's unpredictability into a testament of enduring design. This resilient, practical knowledge was far too valuable to be lost, and its preservation required a system as ingenious as the buildings themselves. A single surviving parchment from the 13th century holds the geometric heartbeat of an entire era. This is the portfolio of Villard de Honnecourt, a traveling master mason whose sketchbook is a window into the medieval mind. Its pages are not filled with lengthy texts, but with a cascade of compass-drawn diagrams, sketches of sawmills, perpetual motion machines, and the precise geometric layout for a rose window. In an age where knowledge was largely passed from master to apprentice by word of mouth and direct demonstration, manuscripts like this were the exception, the vital repositories that preserved complex ideas across time and distance. They were the portable libraries of the craft, the textbooks that allowed a master from Picardy to teach a principle to a mason in Bavaria without ever meeting him. These documents were intensely practical. A diagram might show how to use similar triangles to calculate the height of a tower, or how to inscribe a pentagon within a circle to generate the proportions for a vault. They blended empirical knowledge, the tricks that worked on the building site, with the pure theory of geometry. This was not just art, it was a technical manual for turning abstract lines into physical reality. Very few of these manuscripts survive, as they were used until they fell apart, their secrets absorbed into the stone of countless buildings. But the ones that remain, like Villard's, reveal a culture of relentless curiosity and shared innovation. They show us that medieval engineering was not a collection of static rules, but a living, evolving discipline. A master would record a successful solution to a structural problem, and a century later, another mason annotating the same manuscript might refine the idea further. This continuous cycle of recording, adapting, and improving created a consistent geometric language that could be understood from Paris to Prague. It meant that a master arriving at a new cathedral site, perhaps carrying his own precious portfolio, already shared a common vocabulary with the local lodge. This dissemination of codified knowledge is what enabled the Gothic style to sweep across Europe with such breathtaking speed and coherence. The impossible was not built by isolated genius. but by a continent of builders speaking the same geometric language, their collective wisdom slowly accumulating in the lines of these fragile, priceless pages. You step from a Romanesque church into a Gothic cathedral, and the world itself seems to change. The first space is a fortress of faith, its thick walls pierced by small windows, the air cool and heavy. The ceiling is a massive, rounded barrel vault of stone, pressing down with palpable weight. Then you cross the threshold into the Gothic nave. Light pours through walls of colored glass, and the ceiling soars to a dizzying height, held aloft by a delicate-looking web of stone ribs. This transformation was not a matter of style, but a geometric revolution. The rounded arch of the Romanesque, a perfect semicircle, was a bottleneck. Its shape pushes its immense load powerfully outward, demanding those thick, solid walls to contain the thrust. The Gothic pointed arch, born from the intersection of two circles, is a geometric escape from this limitation. Its steeper angle channels more of the crushing weight vertically down into the piers, drastically reducing the dangerous sideways push. This single geometric innovation unlocked the potential for height. With the lateral thrust tamed, walls could stretch skyward without immediately threatening to split apart. But the revolution did not stop with the arch. The solid stone barrel vault was replaced by the ribbed vault, a skeletal framework of pointed arches intersecting high above. This ribbed cage of stone concentrated the ceiling's load and directed it with precision to specific points on the floor. Suddenly, the wall was no longer a continuous load-bearing surface. It could be peeled back, its stone replaced with vast, luminous panels of stained glass. This geometric shift found its first and most deliberate expression at the Abbey of Saint Denis, just north of Paris in the 12th century. Under the guidance of Abbot Suger, the choir was rebuilt with pointed arches, ribbed vaults, and radiant stained glass windows. It was a conscious experiment in using geometry to dematerialize the wall and flood the sacred space with divine light. The result was so stunning, so spiritually electrifying, that within a generation, the geometric principles pioneered there were being replicated and refined across Europe. This was not a slow evolution of taste, but a rapid technological leap, all driven by a deeper understanding of how circles and triangles could be combined to conquer gravity itself. The race for height and light was on, a race fueled by geometry, and this same relentless geometric thinking would soon be applied to a very different challenge, not of reaching for heaven, but of defending the earth. A castle keep is a fortress in miniature, its entire form a brutal exercise in applied geometry. Its walls are not simple barriers, but complex geometric shapes engineered to turn away any assault. Square towers, while easier to build, created dangerous blind spots at their corners where attackers could gather unseen. The solution was the circular or polygonal tower. A cylinder presents a continuous, curved surface to an enemy, eliminating any sheltered angles. A stone hurled from a siege engine is more likely to deflect off a rounded wall, and miners trying to undermine the foundation found no convenient corner to target. This was geometry as active defense, a shape that literally shed threats. Within these towers, the spiral staircase is a geometric marvel of controlled violence. Nearly all were built to ascend in a clockwise direction. Why this specific orientation? It was a deliberate calculation to favor the defender, who would be standing on the steps above. As a right-handed attacker struggled upward, his sword arm would be cramped and obstructed by the central stone newel post. The defender, meanwhile, had the entire, open well of the staircase to wield his own weapon with full, sweeping force. This seemingly simple curve was a life-or-death geometric advantage carved into stone. Even the smallest openings were governed by this logic, an arrow slit is not just a vertical crack in the wall. Its cross-shaped design, with a wide embrasure on the inside narrowing to a thin slit on the outside, is a precise geometric funnel. It gives the archer inside a wide field of fire while presenting an incredibly small target to enemy bowmen. The angle of these slits was carefully calculated to cover specific zones of the killing field outside, creating interlocking fields of archery that left no safe approach. The mighty White Tower of London exemplifies this total geometric control. Its massive walls, their thickness determined by formulas for resisting battering rams, are punctuated by these strategically placed slits. Its staircases twist in the predictable defensive pattern, and its entire layout is a lesson in layered protection. Every geometric decision, from the grand shape of the tower down to the angle of a single loophole, was a deliberate move in a three-dimensional game of chess against a besieging army. This relentless focus on security through shape transformed a noble residence into an impregnable stronghold, a place where geometry was the ultimate guardian. Yet this same intellectual discipline, this mastery of form and proportion, was also being directed toward a very different goal, not of repelling enemies, but of creating spaces of breathtaking beauty and light in the great halls and chapels of these very same castles. Look closely at the carved stone leaves crowning a cathedral column. What seems like a free-flowing imitation of nature is in fact a hidden geometric grid. Each curling vine and unfolding leaf is meticulously arranged within a framework of invisible circles and arcs, all generated by the mason's compass. This was not mere embellishment, it was a disciplined art where beauty was governed by the same mathematical principles that ensured the building would stand. The master mason would first inscribe the geometric skeleton onto the stone block, a series of concentric circles and radiating lines. Then, within that rigid armature, the carver would release the organic forms, allowing the foliage to spiral out from the center in a rhythm that felt both natural and divinely ordered. This fusion of rigid geometry and flowing life created a powerful visual harmony, a microcosm of the cathedral's grand purpose to unite the earthly and the heavenly. The famous cloisters of Monreale Cathedral in Sicily offer a breathtaking case study. Here, every column is unique, a riot of carved patterns where diamond shapes, chevrons, and intricate spirals dance across the surface. Yet this apparent chaos is an illusion. Each design is built from a finite set of geometric operations, repeated and mirrored to create an infinite-seeming variety. Your eye follows these repeating patterns along the arcade, pulled into a meditative state by the rhythmic pulse of circles and interlocking shapes. This was a deliberate spiritual tool, using geometric repetition to calm the mind and elevate the soul, guiding it from the distraction of the worldly toward the contemplation of eternal, perfect forms. Even the simplest decorative molding, a series of hollows and rounds running along a wall, was defined by compass-drawn curves. These profiles were not arbitrary, they were standardized geometric sequences that created plays of light and shadow, giving weight and definition to the architecture. This pervasive application of geometry, from the grandest vault to the smallest detail, proves that for the medieval craftsman, there was no separation between structure and ornament. The decorative leaf on the capital and the arch that soars above it were born from the same intellectual and spiritual source, two expressions of a single, unifying geometric truth. This profound belief that beauty and structure were one, and the same would ultimately lead them to their most ambitious and perilous geometric experiments. High above the congregation, the stone ceiling blossoms into a complex web of intersecting arches. This is the rib vault, a geometric skeleton that transformed the very nature of architectural space. Its brilliance lies not in adding mass but in subtracting it intelligently. The master mason began with the basic pointed arch, the fundamental unit of vertical thrust. He then repeated this form, crossing two arches diagonally across a square or rectangular bay. These were the diagonal ribs, the primary innovation. By crossing the square space, these ribs effectively subdivided the ceiling into four triangular sections. This geometric act was transformative. The inherent stability of the triangle now governed the entire bay, channeling the ceiling's immense weight along the elegant curves of the ribs and directing it precisely downward to the four corner piers. This skeletal framework meant the spaces between the ribs no longer needed to be filled with thick, heavy stone. Instead, they could be infilled with much thinner, lighter panels, dramatically reducing the overall weight of the ceiling and the outward thrust it generated. This was geometry as a weight-saving technology. The true genius of this system was its modularity. A single, geometrically perfected bay could be designed on the tracing floor and then repeated endlessly down the length of the nave. Each bay was a self-contained structural unit, yet when placed side by side, they created a powerful, rhythmic progression that pulled the eye and the spirit toward the altar. The geometric rules governing one bay guaranteed the stability of the entire vaulted hall. The proof of this concept can be seen in the shadowy grandeur of Durham Cathedral. Here, in the early 12th century, builders constructed some of the world's first high stone rib vaults over the cathedral's nave. The diagonal ribs soaring across each bay were not just structural, they were a declaration of a new geometric order. This system allowed the ceilings at Durham to span a wider space than ever before, creating an interior that felt both monumental and surprisingly open. The success of Durham's vaults gave subsequent builders the confidence and the geometric template to reach even higher, to experiment with more complex patterns, and to ultimately replace solid, oppressive stone with walls of glorious stained glass. The rib vault turned the ceiling from a heavy lid into a dynamic, weightless seeming canopy, a direct result of understanding how to use intersecting circles to create a stable network of stone. This meticulous attention to structural systems extended beyond the grand arches, down to the very machines that made such heights possible. That temporary wooden skeleton, the centering, held the entire future of an arch in its delicate framework. Before a single stone of a vault could lock into place, a master carpenter had to build this intricate falsework, a perfect geometric template shaped to the exact curve the mason had drawn on his tracing floor. It was a structure designed for its own destruction, built with the sole purpose of being rendered obsolete. The precision of this carpentry was as vital as the stonework itself, for the centering dictated the final, permanent shape of the arch. Every rib of the wooden frame was cut and joined to mirror the compass-drawn arcs of the master plan. When the masons then laid their stones upon this temporary support, they were not just stacking blocks, they were following a three-dimensional geometric guide. Each stone or voussoir was individually shaped to fit its specific position in the curve, its sides tapered to radiate toward the imaginary center of the arch's circle. The final, crucial stone, the keystone, was driven into the apex, locking the entire assembly into compression. Only then, once the mortar had set, would the carpenters carefully dismantle the centering. The moment of truth arrived in silence as the wooden supports were removed and the arch stood for the first time on its own, a perfect stone curve born from a temporary wooden mold. This process scaled from the smallest window to the grandest bridge. For a multi-arched bridge like the Pont d'Avignon, builders used identical centering frames for each bay. This geometric repetition ensured that every arch was a perfect clone of the last, creating a rhythm of identical curves that distributed weight and water pressure evenly across the entire structure. The reliance on these provisional guides reveals a profound understanding of geometry's role not just in design, but in the very act of making. It was a dance between the temporary and the eternal, where a perfect wooden circle gave birth to an unyielding ring of stone. This tangible, hands-on application of geometric truth in the construction process naturally led the medieval mind to see deeper, symbolic meanings in the very tools they used every day. Your own feet can trace a pilgrimage mapped in stone on the cathedral floor. Unlike a maze designed to confuse, the labyrinth offers a single, universal path, a continuous line that coils and turns back on itself in a complex dance before reaching the center. This was not a puzzle to be solved, but a journey to be experienced, a geometric metaphor for the soul's winding path toward God. Laid out with the same compass used to plan the vaults above, the labyrinth is a masterpiece of concentric circles and regulated meanders. Its design was precise, often following geometric recipes preserved in manuscripts that instructed builders on how to divide a circle and plot the path's 11 or 12 circuits. To walk this path was to perform a physical prayer. Each turn was a deliberate act, the body following a predetermined geometric sequence that calmed the mind and focused the spirit. The very act of moving through this sacred geometry was believed to align the pilgrim with the cosmic order, the same mathematical harmony that governed the stars and the cathedral's own proportions. The most famous example, the labyrinth at Chartres Cathedral, is a perfect circle containing a complex cross-shaped pattern within its winding path. This is no accident. The cross integrates the earthly symbol into the divine circle, while the 6 petals at its center evoke the 6 days of creation. Every step walked within this design was a symbolic journey through a microcosm of the universe, a universe built from geometric truth. This transformed the abstract principles of sacred geometry into a direct physical encounter. Believers did not just look at the divine ratios, they walked them, embodying the proportions with their own movement. The engineers and masons who embedded these patterns into the floor were creating a ritual machine, a device where mathematics and mysticism fused into a single, transformative experience. This profound integration of geometric order into the very rhythm of spiritual life demonstrates a worldview where measurement and meaning were inseparable, a principle that would soon extend beyond the church walls to shape the flow of water and the layout of entire cities. A straight Roman road cuts across the countryside, its unwavering line aimed directly at the city gates. This was not a relic left untouched, but a testament to a continued tradition of geometric planning that shaped the very arteries of medieval life. Surveyors used their Gromas and sighting rods to extend these roads with the same precision they applied to a cathedral's foundation, plotting the most efficient route between 2 points. A perfectly straight road was not just about speed, it was about economics, reducing wear on cartwheels and the effort needed to move goods, thereby fueling trade and communication across the realm. This geometric rigor was even more critical for the lifelines hidden beneath the streets. Aqueducts and drainage channels could not rely on guesswork. A master of waterworks used simple geometric tools to ensure a consistent, gentle gradient from the source to the city. His level was often just a long, water-filled trough, showing him the true horizontal plane. With it, he could calculate the precise slope needed to keep water moving steadily, neither stagnating nor flowing with such force that it eroded the channel. A miscalculation of even a single degree over a long distance would mean the system failed entirely. In Canterbury, the intricate water supply system fed public fountains and flushed away waste through carefully engineered conduits. The cross-sections of these channels were not random. They were precise geometric shapes, often semicircles or segments of circles, designed to maximize flow and minimize sediment buildup. This geometric foresight prevented blockages and contamination, directly impacting public health in crowded urban centers. The public fountain in a town square was more than an ornament. It was the geometric endpoint of this calculated journey, a symbol of a community's ability to harness natural forces through mathematical order. This practical, earth-bound application of geometry sustained the daily lives of thousands, proving that the compass and straightedge were as vital for public health as they were for spiritual aspiration. And this same universal language of lines and angles was simultaneously being used to design sacred spaces far beyond the borders of Christendom, in the soaring minarets and intricate mosaics of the Islamic world. A cloister's arched walkways frame a garden in a perfect square, a living diagram of divine order. Monasteries were not just places of prayer, they were meticulously planned communities where geometry structured every hour of the day. The entire complex followed a grid system, a geometric module repeated for the church, the chapter house, the refectory, and the dormitories. This was architecture as a spiritual discipline, where symmetry and proportion were believed to cultivate inner harmony and focus the mind on God. The cloister itself was the geometric and spiritual heart. Its central garden or garth was a symbolic paradise, a bounded piece of nature ordered by human reason and divine law. Walking its covered arcades, a monk would meditate within a perfect square, his physical path mirroring his spiritual journey toward clarity and peace. Every element reinforced this sacred geometry. The church was precisely aligned on an east-west axis, its proportions often based on the square and the square root of 2, ratios thought to embody cosmic balance. The famous plan of St. Gall, a 9th-century architectural drawing for an ideal monastery, reveals this philosophy in stunning detail. It is a complete geometric blueprint for a self-sufficient community. The church is the central module, and every other structure, from the infirmary to the workshops, is plotted in relation to it using a consistent geometric grid. This ensured a harmonious and efficient flow between the monks' sacred duties and their daily labors. The bakery was geometrically proportional to the brewery, and the scribe's desk was positioned to catch the light at an angle calculated for maximum clarity. This was geometry applied to the whole of life, creating an environment where faith and function were seamlessly interwoven. The very stones of the monastery whispered a lesson in orderly living, a quiet testament to the belief that a well-ordered soul required a well-ordered space. This profound integration of design and daily ritual was only possible because the master mason possessed a deeply personal and portable toolkit for turning these abstract grids into tangible reality. A mason's square feels heavy and certain in your hand, its 2 arms meeting at an unyielding 90-degree angle. This simple tool was far more than a piece of metal. It was the physical embodiment of truth in the medieval building world. Where the compass created the divine curves of heaven, the square imposed the order of the earthly realm, ensuring that every wall rose perfectly vertical and every stone met its neighbor at a true right angle. This was the baseline of all construction, the non-negotiable standard that prevented a building from leaning into ruin. Without the absolute certainty of the square, the most complex geometric vaults and arches would have collapsed into chaos. The tool itself was often a work of art, its surface etched with intricate geometric patterns, scales, and sometimes even secret symbols. These were not mere decorations, they were functional references. A master might have one square with markings to quickly lay out the proportions for a window, and another with a different set of divisions for determining the taper of a spire. This customization made each square a personal calculator, its secrets known only to its owner. In the emblems of the stonemasons' guilds, the square is always present, often paired with the compass. This pairing was deeply symbolic. The square represented morality, honesty, and the right action of the builder in the material world. To be on the square meant to be trustworthy and true. This ethical dimension was inseparable from the practical one. A mason who could not be trusted to be honest in his dealings could not be trusted to build a true wall. His geometric precision was a reflection of his inner character. By mastering this handheld instrument of perfection, a single craftsman could ensure that the grand geometric vision conceived on the tracing floor was executed with flawless integrity across an entire cathedral, from the deepest foundation to the highest spire. This intimate relationship between the builder, his tools, and his code of ethics infused the cold logic of geometry with a deeply human purpose, a dedication to truth that was literally set in stone for the ages. The dome of Florence Cathedral was an architectural problem no one knew how to solve. For decades, the massive octagonal base sat open to the sky, a challenge that seemed to defy the engineering knowledge of the age. When Filippo Brunelleschi won the commission, he did not cast aside the past. He looked directly back to the geometric principles of the medieval masters. His brilliant solution for the dome was not a rejection of Gothic thinking, but its ultimate evolution. He essentially constructed a double-shelled dome, an idea with its roots in the layered structures of earlier centuries. But its true secret lay in its herringbone brick pattern, a self-supporting spiral that locked each course of bricks into the one below. This was a direct geometric descendant of the rib vault, where intersecting arcs create a stable, self-buttressing skeleton. Brunelleschi had studied the great Gothic cathedrals and the surviving manuscripts that preserved their methods. He understood that geometry was not a set of rigid rules, but a dynamic language for managing weight and force. His dome was a monumental fusion, blending the classical ideal of form with the medieval genius for structure. This was the dawn of the Renaissance, but its engineering soul was still deeply Gothic. Architects and artists began scouring monastic libraries for forgotten portfolios, recovering the geometric secrets that had built Chartres and Amiens. They realized that these methods were not primitive but profoundly sophisticated. The same proportional systems that dictated the height of a nave were now applied to the facades of Renaissance palaces, creating a new harmony in secular architecture. The vertical aspiration of the Gothic cathedral was translated into the horizontal grandeur of the piazza, all governed by the same sacred ratios. This was not a break with tradition, but a continuation. The geometric thinking that allowed a flying buttress to channel thrust was the same logic that allowed a dome to seemingly float over a city. By building on this medieval groundwork, Renaissance engineers expanded the very possibilities of design, proving that the most powerful innovations often stand on the shoulders of forgotten giants. The legacy of the master mason's compass and straightedge was just beginning its long journey into the future. A modern architect stares at a screen where lines and curves generate themselves according to a set of digital rules. This parametric design process, for all its computational power, is a direct echo of the medieval tracing floor. The software operates on geometric algorithms, complex sequences of if-then commands that dictate form. A medieval master used his compass to execute a different kind of algorithm, a physical sequence of steps that, when followed, generated the perfect proportions for a vault or a window. Both methods are rooted in the same powerful idea that beauty and stability emerge from a set of underlying geometric laws. This is not a coincidence, it is a rediscovery. Modern engineering is now relearning the medieval lessons of proportionality and material efficiency. Just as a Gothic mason used the absolute minimum of stone to achieve maximum height and light, today's architects use computational analysis to create structures that use the least amount of steel or concrete, reducing both cost and environmental impact. The goal is identical: to build more with less. We see this principle brought to life in stunning contemporary projects. The soaring roof of the British Museum's Great Court, a vast glass canopy supported by a delicate-looking web of steel, is a direct descendant of the Gothic rib vault. It achieves that same breathtaking sense of lightness and transparency by intelligently distributing forces along a geometric skeleton, just as the medieval builders did. Even the undulating, organic forms of buildings designed by architects like Zaha Hadid are not random. They are generated by complex algorithms that optimize structural performance and environmental factors, a high-tech version of finding the perfect natural curve. Experts in sustainable design point out that these medieval principles are more relevant than ever. Their buildings were inherently sustainable, crafted from local stone and designed to last 1,000 years, a stark contrast to the wasteful cycles of much modern construction. By re-embracing this ancient wisdom, we learn to blend art and science once more, creating spaces that are not only functionally resilient but also spiritually uplifting. The cold logic of the algorithm, when guided by a sense of timeless proportion, can produce works that inspire awe, just as the cathedrals did. This proves that the geometry of the compass and straightedge is not a relic, but a timeless guide for building a better world. The very fact that we are returning to these ideas after centuries of technological change suggests that the medieval masters discovered something fundamental about the universe and about ourselves, a mystery whose edges we are only just beginning to trace. The true depth of their geometric mastery might be measured by the mysteries that still resist our understanding. Take the precise solar alignment of Chartres Cathedral. On the summer solstice, a specific spot of light falls through a labyrinthine window to illuminate a single stone in the floor, a feat of celestial geometry that seems to encode advanced astronomical knowledge. How did they achieve such accuracy over such a vast scale, with only their simple tools and the stars to guide them? This is not an isolated puzzle. In certain chantry chapels, the geometry of the vaults and walls creates perfect acoustic resonances, amplifying the human voice in ways that modern sound engineers struggle to fully explain. Were these sonic miracles deliberate, or a happy accident of a design focused on structural and symbolic harmony? We find similar enigmas woven into the very fabrics that adorned these spaces. Medieval tapestries often conceal complex geometric grids beneath their pictorial narratives, patterns that may have served as both a design blueprint and a hidden symbolic code, a language of proportion meant to be felt as much as seen. The most enduring debate among historians centers on whether these achievements sprang from lost, meticulously recorded techniques, or from an intuitive genius honed by a lifetime of working directly with stone and line. This intuitive grasp might explain the fluid, complex curves of some spiral staircases, for which no clear geometric recipe has ever been found in surviving manuscripts. The builders may have carried the most sophisticated formulas not in their books but in their hands and minds. By acknowledging these unsolved puzzles, we do more than admit a gap in our historical record. We pay tribute to the profound and perhaps unknowable synergy between rule and intuition, between sacred number and human touch, that gave these structures their enduring soul. This lingering sense of wonder before their work forces a final, broader question. What was the ultimate role of this geometric language, if it could simultaneously chart the heavens, orchestrate sound, and conceal secrets in thread and stone? This geometric language was not confined to the cathedral or the castle. It was the silent engine of an entire civilization. From the soaring vault to the carpenter's square, from the layout of a city to the trajectory of a trebuchet stone, the same set of rules provided a unified system for innovation. This was a world where art, science, and engineering spoke the same vocabulary of lines and circles, allowing a master to move from designing a stained glass window to reinforcing a city wall with the same intellectual toolkit. The consistent application of these principles meant that a breakthrough in one field could ripple through all others. A new method for calculating thrust in a bridge arch could be adapted to strengthen a cathedral's nave, and the geometric patterns perfected in a monastic cloister could inspire the defensive layout of a new town. This created a powerful cumulative effect. Each generation of builders did not have to start from scratch. They inherited a living, evolving body of geometric knowledge, refining the proportions of a vault or the curve of an arch based on the successes and failures of their predecessors. This is why the Gothic style could evolve with such breathtaking speed across Europe, a continent-wide conversation conducted in a shared geometric tongue. Experts who study this period point to this holistic system as the true catalyst for medieval innovation. It was not a collection of isolated tricks, but a coherent framework for understanding the world. This geometric backbone gave them the confidence to attempt the impossible, because they trusted that the same logic that governed the heavens would also hold their stones in place. By viewing every challenge through this singular lens, from the grandest urban plan to the simplest machine, they turned geometry into the very language of possibility. Their legacy is not merely a collection of beautiful old buildings, but a profound demonstration of how a unified system of thought can empower humanity to reshape its world. A single name, Villard de Honnecourt, survives from the legions of masters who shaped the medieval skyline. His portfolio is a rare and precious window, but for every Villard, there were hundreds of others whose names have vanished into the stone they carved. These were not anonymous laborers, but brilliant individuals whose creativity and patience translated the cold logic of geometry into a living, breathing reality. They began their journey as young apprentices, spending years mixing mortar and hauling stone before ever being allowed to touch a chisel. This long initiation was not just about learning a trade, it was about absorbing a culture, a way of thinking where every action was measured against an ideal of geometric truth. A master mason was more than a builder. He was a designer, an engineer, and a manager, responsible for a workforce of hundreds and a budget that could rival a king's ransom. He had to possess the vision to see a finished cathedral in a few lines scratched on a floor, and the practical wisdom to solve problems that no manuscript could predict, like a foundation settling on unstable ground or a shipment of stone that arrived with hidden flaws. Their work was a testament to profound collaboration. The master mason who designed the vaults worked in constant dialogue with the master carpenter who built the intricate centering and the blacksmith who forged the specialized tools. Each relied on the other's geometric understanding to ensure their pieces of the puzzle fit together perfectly. A chronicler from the time of Chartres Cathedral wrote of the masters there. They worked with a fire in their minds, and their hands were guided by a love of the art. This was not a dry, mathematical exercise. It was a passionate, human endeavor. Their genius lay in knowing when to follow the geometric rules absolutely, and when to adapt them intuitively, shaving a millimeter off a stone or adjusting an angle based on a lifetime of feeling how weight and thrust moved through a structure. They left their mark not in signatures but in the subtle flourishes of a carving, the unique profile of a molding, or the daring leap of an arch that no one had attempted before. To stand before a Gothic cathedral is to stand in the presence of these forgotten minds, to feel the enduring power of human ambition channeled through the disciplined language of shape and number. Their legacy reminds us that the most timeless structures are born not from formulas alone, but from the harmonious union of human spirit and geometric truth. From the compass's first arc to the cathedral's final stone, geometry served as a profound catalyst for the medieval mind. It was the language that turned impossible dreams into immortal stone. We have walked through the shadowy aisles where sacred ratios gave form to light, and stood atop castle walls where the stable triangle defied destruction. We have witnessed how the simplest tools unlock the most complex designs, not through magic, but through a disciplined framework of innovation. This legacy is not confined to history books. Look at the steel and glass of a modern skyscraper, its skeleton a direct descendant of the Gothic rib vault. See the elegant curve of a suspension bridge, a principle of tension and compression first mastered in stone arches centuries ago. The medieval engineers left us more than beautiful ruins. They gifted us a timeless dialogue between mathematics and imagination, a way of thinking where beauty, strength, and meaning are woven from the same geometric threads. Let this journey change the way you see the world. Notice the proportions of a window, the curve of a staircase, the hidden stability in the structures you pass every day. Their geometric language is all around us, a quiet testament to human ingenuity. If this voyage into the past has illuminated new perspectives for you, share your thoughts below. Subscribe to continue exploring history's hidden wonders and carry with you the enduring lesson that with the guiding light of geometry, even the impossible is always within reach.